Joe. Sup everybody, welcome back. Today we're surrounded by plastic toys. Welcome back everyone. My name's Andrew, this is the Make It and Break It YouTube channel. And on today's episode we're making another entry in the 3D Printing Basics series. We're talking about what you can do with a 3D printer. So our previous couple episodes have been things like what is 3D printing? Going through some of the definitions, terminology, so when we discuss it, we're starting from the same basic standpoint. And then also, what do you kind of need to get into 3D? I think I did a little bit backwards, where instead of starting with what you need to do 3D printing, I probably should have started with what can you do with 3D printing? Because at the end of it, we all really care about what are the cool things we can do with it, not necessarily exactly what we need right off, because we can go Google that. So today's video, we're going to go through some of what I consider the major categories of functions of 3D printing, major things you do with them. They can all kind of interchange with each other. There's definitely no like hard line, this is one thing, this is another. This is how I would kind of classify the various processes and inputs and outputs for 3D printing in the motorsports arena, industrial arena, even in your home garage area. So that's kind of where we're going at today. We're going to try and keep a fairly consistent format here. So we're going to talk about the category, give like a general description of what it is that I have in front of me, and B-roll from around the garage area and all of my workshop area. Examples of most of these items. There's one of them I don't really have a good example for, but that will be coming later on when we get to doing a little bit more of the cool fabrication type stuff with this technology. So a few things to keep in mind. I'm going to be coming at this from the perspective of an FDM printer. Fused deposition modeling. If you're confused about what that means, then go see our first video. We'll send a card or something like that here. And there's the terminology and all that sort of stuff is discussed in that video. There are other types of printing out there, other types of additive manufacturing that have similar material functions and the ability to do very similar things. I'm just going to stay in one framework for now, and if you guys have questions about that, definitely throw those down in the comments below. The other thing is we're going to discuss some materials in general, but this is not a materials discussion. That'll probably be our next video. So if you're looking for a real in-depth discussion on the attributes of PLA versus ABS, then that won't be here. This is more of an applied, what can you do with this, and some general ideas of the types of materials you should be looking at. With that in mind, since I'm surrounded by plastic parts that I've made, in fact even some of the stuff that's holding up the stuff on the wall behind me is plastic parts that we've made, let's get into it with our first category, which is useless figurines. Useless figurines. This is a category I bring up not because it's necessarily useful in a motorsports home garage type environment, unless you're building like dashboard hula girls, in which case you hit the right spot. This is kind of the hobbyist sort of thing. People find cool little figurines. This is a test print from one of my printers that I brought out. It's kind of a cool little print. It's actually really well calibrated. So I'm actually very impressed with that. This is kind of the typical idea. People think, hey, 3D printing, where they're making like stupid little figures and completely useless parts, and some people do. In fact, I've actually done some I actually looked at trying to do a print for a cosplayer, a friend of mine, that was a full light-up Zelda sword of some sort. I'll try and throw a picture right over here. And a lot of people do that, and it's a really cool way to use this technology. But this useless figurines is really just kind of a catch-all for hobby use. A lot of people who have a hobby use, they make figurines or miniatures or whatever. It's really cool. You can get some great results from it, but it doesn't really help us in the motorsports and home garage type world. So the first category that actually helps us here is a category that's called prototyping, or rapid prototyping. So the 3D printer technology and additive manufacturing in its conception in the late 80s, early 90s was really only useful, or only thought of useful by the industry, as a prototyping tool, or something that would shortcut the time to build new concepts or ideas. I think the phrasing is useful for aesthetic or functional prototyping. something like that. The idea being, if you have something that can easily just take a data module, which is your just data file, your CAD file, and create it from nothing, you don't have to take up your machinist's time or come up with special tooling to make these things, to go figure out if it fits, if it works, does it look right, all that sort of thing. Hi, Joe. Prototyping has a lot of uses in motorsports because we're doing stuff with cars that they weren't originally designed for, so we have to come up with new parts. And a lot of the best ways to conceptualize, thank you, Joseph, for the tail. Don't give me that look. Oftentimes you have to go through several iterations of a design before you get something that you really like. And it's a lot easier to use a 3D printer to create iterations of your design than it is to go back to the lathe and go spend hours on a new iteration just to go check it if you're not even sure it's going to work. Of these things that are sitting up here, this is actually, this little green thing, is a prototype. So if you remember way back at the start of this channel, I was working on my Chrysler 300C and I broke the hood latch pull tab. And I needed a replacement because obviously you need to be able to open the hood on a car. So I sketched up this thing, which is a 2-piece pull tab prototype. And I actually sketched it up in about 45 minutes, just taking some rough measurements on my head and trying to think through it. And I sent the file over to my friend who had a pretty good 3D printer, and I was working with him at the time. And he printed it for me that night, and next day I got it and checked it out and took it over to the car and figured out that some of the holes, the interior holes, weren't proper, and the interferences with the two pieces where they clamped together meant you could never unclamp it, which I ended up deciding was not a bad thing, but I originally wanted to be able to pull this off at some point or another without totally destroying the piece. So instead of taking this CAD file and going off to a machine shop or chucking it on a lathe myself, which would be difficult with some of the features on here, I just tossed it to my friend. He printed it in a couple hours, brought it all back, and I had my prototype that I could go take to the car and test out. So this is one of the ways I'd expect most people to use these, because a lot of the parts you're going to make with a 3D printer, at least initially in plastic, you might want to make in metal for the final form. But this is a really good way to test out your ideas and your solutions without wasting a bunch of mechanic time or manufacturing time or even a lot of money, because this is like 15 cents worth of plastic. So a quick discussion about materials. Prototyping, unless you're prototyping a flexible hinge-like material, then there's specialty flexible materials that you could use. Most prototyping is done with PLA, which stands for polylactic acid. It's one of the most common plastics available for FDM 3D printing. It's very cheap. It's used because it's cheap. It's used because it prints very easily and inexpensively on essentially any machine in the world. And there's a lot of knowledge base on how to get it to do what you want to do. And most prototypes are not subjected to the stresses that would cause PLA to fail. So PLA is pretty standard prototyping material. If you're really fancy like my former employer and the cheapest printer you have is a Stratasys 450 MC or whatever it is, their entry-level material is an ABS style material. That is also fine for prototyping. It's been printed for years. It's just got properties that are usually overkill for most prototypes. Another prototype type use is kind of a display model. So those of you who are trying to sell products, or if you're trying to describe a problem to someone, you can actually print models of both the problem or the component or the car and show what your product does and that sort of thing. So that's more of a product management or a product display type thing, but that was a very wide spread use of 3D printing technology in my former employment, where we had very complex problems or problems that required explanation. Visual explanation is often the best way to explain it. So we would have models printed of the various things we worked on and use that to explain what we were working on and why we were working on it to interested parties, for example. So we're going to move past prototyping to the first functional area of 3D printing, and that's tooling. So tooling is kind of what it sounds like. It's tools that help you get the job done or make getting the job done easier. So I tend to consider tooling anything that supports putting the final product in or supports storing final product, but is not itself final product. So that includes things like this monitor stand right here that I printed back in my setup video. You can see this here, as well as things like this, which is my wheel clearance tool I use. This is I took a drawing from Method Racing Wheels, and created a tool that I can mount to the hub of a car. This one's set up to mount to my RX-8 and check wheel clearances by rotating the wheel hub around and seeing if it hits anything. So there's a bunch of different tooling style things. Some other things around the office that we've done that I would consider tooling are my motorcycle helmet wall mounts and my motorcycle stand ceiling mounts. So these things keep and hold my tools in the right spot, and that's what I would consider a tooling application. There's two types of tooling, really, that get used. There's non-critical tooling, which is tooling that gets used in a low-stress application or gets used for low-risk components. That is pretty much all the tooling that we've used. So this is just a monitor stand. It's very low stress. It's only holding whatever those monitors weigh, 7, 8, 10 pounds, something like that. And this is essentially a no stress, just interference piece where the structural integrity of the piece doesn't really matter. Similarly, the helmet mounts and the motorcycle stand mounts that I showed earlier, pretty low stress, only 5 to 6 pounds or maybe 10 pounds at the most on the motorcycle stand mounts. And it's not like if they fail, I'm going to be out several thousands of dollars or have a motor blow on me or something like that, go wrap something around an axle of the car. So it's not like a critical application where the failure comes with a high risk of serious damage. Non-critical tooling is usually constructed out of low-cost materials that are easy to print. So things like PLA, which is actually pretty much everything I've printed around here is PLA. ABS, depending on what you need, maybe an ASA. But these are all low-cost materials. They don't have the highest mechanical properties, and sometimes they're a little bit vulnerable to chemicals. So if that is an application that you need, you might consider a different material. But low risk, low stress applications like non-critical tooling, those materials work just fine. Obviously, if we have a non-critical tooling section, there's also a critical tooling segment. This is tooling that is either a high stress or requires high strength or high mechanical or chemical resistance, or is kind of high risk where you can be, if it fails, you are into a lot of monetary or time damage. In industry, critical tooling is 3D printed in places like robot factories, where specialty gripping arms are usually needed for various different points. So instead of sending out and waiting a very long time for a brand new specialized gripping arm made out of aluminum or steel or whatever, they can throw a new design for a 3D printer and print out in a durable, strong plastic or plastic composite type material. In this case, you'd be thinking like nylons or carbon-filled composite nylons or ULTEM or those types of materials. The materials that are high toughness, high durability, high strength, generally pretty stiff if you pick the right materials, that sort of thing. Fixturing is another critical tooling category where 3D printing comes in handy. This is things like fixtures for, say, milling. Let's say I'm trying to mill this thing, and for some reason I mill it, off axis like this somehow. You can actually 3D print yourself a fixture that you can clamp into a vise that will hold this thing in the right area and the right orientation, such that your milling machine will hit the right spots where you need it to be. Or mobile machining guides and things like that. Things that, let's say I'm working on a pipe like this, right? And I need to drill at a certain angle like this. You can actually 3D print a guide that you can put on a piece of pipe where you have to drill at an axis, and then you can use that as a bushing for your drill to go do that. So that would make up something like your critical tooling applications. Materials we kind of already covered. You're going to want your more industrial plastics. Those are your nylons. Those are your carbon nylons, Ultem, polycarbonates. Basically, you're going to want to match your materials to your end-use requirements in this case. The next category we're going to go through is end-use parts. Unlike in the early 90s, we were talking earlier with rapid prototyping, end-use parts are now commonly 3D printed, especially in low-volume, high-mix style of fabrication. This segment of the 3D printing arena is growing larger as the printers become more capable, as people become more able to use the printers and the printing software, and as materials start expanding into much more usable ranges for everyday use and competition use and motorsports use, and even like high-end transportation level use, where parts are now becoming more 3D printed. And just like tooling, there's two basic subcategories here. There's non-critical end-use parts and critical end-use parts. And the material uses are fairly similar, actually. So non-critical parts are, again, low stress, low risk style parts, where your concern might be trying to save on fabrication time or fabrication cost, much less than the end-use strength of the part. So as an example for an end-use part is this. This is a mounting ear or a mount for a Chrysler 300C, basically a whole LX chassis, power distribution module. So a few episodes ago on the Project U Chrysler 300C, we were troubleshooting some electronics, and I found out the car's power distribution module was just hanging out in the engine bay, completely unsupported, probably not doing anything good for our electronics. So I eventually went through a few design changes and came up with this thing, which engages with some ears. So the power distribution module actually inserts into these little bosses here. So it inserts here and then gets bolted in, and then this will get bolted onto the main crossbar on the Chrysler 300C. Pretty easy. There are features on this part that would make machining it difficult or require many machining processes. I've been looking at this a little bit, and I don't think you can mill this out without at least 3 different milling operations. That means setting up your machine, centering it on the piece, milling it, pulling everything apart, recentering it, milling it, pulling everything apart, recentering it, milling it. And that would take a long time, and each time you tried to make it out of metal, you would have to go do that all over again. That's a lot of sunk time into a final part, whereas I printed this part in a few hours. Like this is a very quick print. This is a non-critical end-use product, obviously. It's just holding a computer in place, trying to keep it from jogging all the electronic connections loose. As for critical end-use products, these are high stress, high temperature, high criticality sorts of components. These are things like you probably wouldn't want to make engine mounts out of 3D printed materials, although I'm almost certain that you could in many cases. But these are things like you could make complete alternator mounts out of 3D printed components. You could make things like hose mounts and hose locators and wiring loom mounts, and basically anything you could substitute that's maybe semi-structural or structural underneath the hood of a car, you could probably substitute with a polycarbonate or a nylon carbon fiber composite style material and get the same or better results for much less fabrication time and or fabrication cost. So things like that. In the motorcycle world, I've been throwing around some designs for crash protection. So motorcycles, if you don't want to scratch up your fairings, oftentimes they'll have crash protection, like just pods that are bolted into the frame. So you can actually 3D print out of nylon or sometimes Delrin or some combination, actually 3D print a whole assembly that will go on there, and you can just replace the end units, or 3D print a custom sleeve for like your stunt cage on your motorcycle, for example, where you can put some nylon sliders that will hit and slide and take a lot of the impact before it hits your stunt cage, and then you just replace a slider with a couple screws or something like that, and off you go again. Pretty easy, but those are kind of high impact, high toughness style uses that you really can't get away with using just like PLA, right? So that's kind of the two categories of end use fabrication. The final category is there's no specific title that I could come up with other than Special Fabrication Solutions, which is essentially using 3D printing, using 3D printed models or 3D printed bucks or 3D printed molds to help create metal parts, for example, if you're trying to cast some parts, or even composite carbon fiber, fiberglass style parts. So this is taking advantage of the ability of 3D printing to print intricate one-piece parts, or to go into a computer design a multi-piece assembly and then just send parts of it to a 3D printer so that you're sure everything's going to go back together and none of it was hand fit, such that you might have little gaps and issues. You have much more precision in your end product. And so this category is a little bit more nebulous, and it's kind of hard to describe unless I go get something real quick. Hold on. I brought for show and tell today a Mazda RX-8 exhaust manifold. This is kind of a show and tell item. This is not necessarily the only thing you can do, but it presents some of the problems that you can try and address with 3D printing. So manifolds like this, intake and exhaust manifolds, are typically cast items, right? So they're cast aluminum or cast steel. You can actually help reproduce them or produce your own substitutes with 3D printed materials, and that's done in a couple ways. One, 3D printing materials in industry, like no joke, people who get paid lots of money by big companies to go do this sort of stuff, they can use 3D printed materials to create molds for doing things like casting steel and stainless steel. Typically that's actually done with PLA because it burns clean. This is very similar to the lost wax investment casting style of casting, where you would take a 3D printed component like this, you go do your prototyping steps where you go install it, make sure it fits, it looks like it's going to be right, the computer models say the strength will be right when it's in the right material. You send it off to someone, or you do this yourself if you're a home DIY guy, kind of like me. You send it off, and they will take this part and put it in, they'll like dunk it and make this big whole like ceramic thing around it, right? And then they'll burn out the plastics on the inside. So you have this big ceramic pot type thing with a void in the middle that looks exactly like the part you want, and they just pour the metal in. I think Siemens is who I think I was reading about using this. They make like 3/16 stainless steel parts that way, and it cuts their fabrication time down from 12 to 16 weeks to go make their own molds and casts and all that sort of stuff to 1 to 2 weeks when they do all their engineering, figure out the piece of work, send it out, company does the casting for them, and it's back in 2 weeks. So something like this, let's say you wanted to cast this, I could 3D print most of this in a PLA style material, find a company who would do some lost wax casting for me, and they could set this whole thing up so that I could cast my own exhaust manifold. I don't necessarily want to. I have a welder and tube bender for a reason. But if I were looking for some really complex shape that's really hard to make on a tube bender, I could go out to someone and ask me to have them cast it in steel and get myself an exhaust manifold back. So that's one way to take your 3D printed parts and the benefits of 3D printing, which allows you to make really large single piece components, and to go out and get metal components or very high strength components built based off of those pieces. The other thing that you can do, and I'm very excited about doing this on this channel, is use 3D printed parts as molds for composite parts. It's usually not exhaust manifolds, but like intake manifolds. A lot of the intake side of a car, for example, you get plastic intake manifolds and upper intake manifolds. Pretty much everything that doesn't touch the combustion part of the engine is all plastic. So a lot of people, for the bling or for some minimal amount of weight savings, mostly for the bling for me, will go make complete carbon fiber like intake manifolds or complete carbon fiber intake tubes. And that can get very expensive, and if you want it to look correctly, the molds can be very complicated. If you were trying to mold this thing, for example, let's say this is an intake manifold, something that sits on top of the engine like that. This would be a very complex, very expensive mold, multi-piece mold. There's a lot of release lines that would be very obvious, and so you have to spend a lot of time and money on your fabrication. And you could accomplish the mold. You go print it in like a finishable material, ABS, something like that, and you could go autoclave it up just fine in that way. You could 3D print it. You'd have to do some handwork. There's no way getting around handwork in molds like that, but you could go out and 3D print your own carbon fiber molds. But my favorite thing for this special fabrication section is internal dissolvable molds. Internal dissolvable molds takes advantage of an actual weakness in 3D printing that's been solved so that you can make cool parts. So when I print this part, I print it in like this orientation or this orientation or this orientation. All of these parts that are just out in the middle of nowhere have to have something that supports them so that it doesn't droop or deform, because essentially what the print head is doing is throwing liquid plastic in the middle of the air, and that's a bad way to create a rigid shape, right? So most printers will do some sort of support material. If you've got a cool printer or you want to spend the money on it, multi-headed printers can print in 2 materials at a time. And so what a lot of commercial printers and my printer and even some consumer level printers now, they actually will print a support material that is dissolvable. So instead of having to go through and like take a pick or pliers and pull out all of the support material on your model that doesn't need it once it's done being fabricated, you actually just take it out and throw it in a bucket of water or a bucket of limonene or something like that. Something that dissolves the support material and it just leaves you with your base part. So that's really cool for making parts like this, but you can apply it for making parts like this manifold. So what you can do is actually design the internal parts of this manifold that essentially fills up the holes of this manifold. So it would make all the parts that are like air pockets where the air is exhausted out in this case, or for an intake manifold where the air follows through and into all of the intake plenums and everything. You can design a part that fits there and all that sort of stuff, and then carbon fiber around it. And this will let you create a nice smooth finish on your carbon fiber. You can hide the seams in places where they won't be visible. Now, where it's a lot easier to do that than if you have a multi-piece part where seams are kind of where they have to be for the mold to release. And when you're done, normally you can't get parts, internal parts like that out of complex shapes out. But if you have a dissolvable part, you just throw it in a vat of water or, you know, whatever solution you need to get it out, and it actually dissolves out of the middle of your part. So you have a part that's essentially impossible to create in normal methods, but you use your 3D printer and some dissolving filament and created this fantastic new intake manifold, or, you know, whatever sort of piece that's basically impossible. So that's pretty much it for our basic overview of what you can do with 3D printing. Remember, you can build cool toys and figurines. You can build yourself some prototypes. You can build yourself tooling, build yourself actual functional end use parts, and use 3D printed parts to help you make molds and casting molds and bucks for casting or composite manufacture. So these are kind of general big ticket items for things you can do. The cool thing about 3D printing and why it's such a powerful tool to go start using in your shop is that you can usually make just about anything you can dream of on a 3D printer. You just need to be able to sketch it up enough that the computer can understand what you want. These categories are not the be all and end all. There's certainly technologies and companies out there doing things with 3D printing that I don't know about, or that are completely revolutionary in the way to use it. These are just kind of trying to bring some of that stuff to you guys so you can then take it to your garage at home and use this technology to help you out in your, you know, on your project car or on your tuner car or whatever you want to go use it. Next up in this intro to 3D printing, next up in this 3D printing basics series, we're probably going to go through some of the major materials out there in FDM style 3D printing, talk through some of their strong points, some of their weak points, some of the drawbacks with using some of them, and try and round out some of this initial discussion of 3D printing. If you have any questions or comments about anything I presented in this video, definitely throw them in the comments section down below. If you like this video, definitely hit like. If you like what we're doing in this channel, we've got 3D printing videos like this. We have motorsports projects like a RX-8 race car. Definitely check that out. Hit subscribe and ding that bell icon so you get notified when we put out a new video. So thanks for watching, everyone. My name's Andrew. This is another Make It Break It YouTube video, and we'll catch y'all later. Joey, come on, let's go.